Hello. This is just I hope it's gonna be short, explaining how I managed to get the angular position of the sun in relation to the Earth. If this is the orbit of the Earth around the sun, and the sun is here, this is the sun focus, and this would be the empty focus. I know this doesn't look like a perfect ellipse as we would expect, but the eccentricity of the Earth's orbit is very tiny. You would see it like a circle, and it's even not to scale this drawing. I had to know the angle of where is the the Earth in relation to the Sun from a starting point of 3rd January, where the sun or where the earth is in its closest path to the sun. I presume that this angle would be 0, and if I put the day, sorry, I have to explain this first. Uh, these are all a bunch of crap equations that I made. I know it looks messy, but that's how I build it, and it was already in a different sheet, and I kept just pouring it into my Sun calc application. Here, this is the starting date, and this is the date that you choose. So let's say 11 October. So it shows 281 days, and right here it's not exactly 281 because I added the angle, the difference between the winter and that point, so I added to that angle. But anyway, this is not the point here. I get this day, there's a slight change, and then that number is transferred into an angle. You see it color coded in red because it's in relation to the empty focus. So on 11th of October, it will be the day 281, and the angle will be 277. So it will be starting from here. It's here, right? This here, almost 20. No, right here. But let's get it to an angle similar to this. So let's say 9th of September. Yeah, that looks better. So 245, that's around this. Now we need to know that red angle is the direction of the Earth from the empty focus. We need it from the blue or the sun focus. So right here you see the I don't know what you call it, aphelion and perihelion, something like that, the closest and the furthest. And here is the eccentricity. And I use a very complicated equation. I don't understand it, but yeah, this one, you see it here in the equation line. This is to calculate the red radius, or the radius or the distance of the Earth from the empty focus. And if I have this, I can get the blue one, or the distance from the sun. And this black 5, this is 5 million kilometers, is this distance. So I use a bunch of equations, and then I get the blue angle. And you can notice here, this angle is 243, 245, and if we put another simple equation here, equal this one minus that one. So the difference is minus 173 degrees. So let's put here 0. The difference is 0. Let's put 180. Oh yeah, 180. We still have a slight difference here. This one. Because the year is not 360, it's 365. So let's say the day 182.5. There you got it. The angle is 0. So the maximum difference between the angle of looking to the sun and looking to the empty focus is when the Earth is around this area. So it's around 270 degrees. So let's say the day 272. Yeah, that's it. You got it. The maximum is around 1 degree, point 91. And let's increase it by 1 day. 273. Still the same. 273. Oh, sorry. 274. 276. 278. 280. I don't know why it doesn't change. 285. No, yeah, now it started to reduce. So that was the maximum at 1 degree, point 91. Um, that difference contributes to the analema, and also the speed change of the Earth when it's in its closest path and furthest path to the Sun also affects the analema. Now let me get the Google Earth. Is there anyone out there? Hmm. Who's watching? I don't know why there's no chat. Anyone there? All right, so back to Google. Oh, Soundly! Oh my God! It's good to see you here. I hope I'm making any sense because I barely understand these things what I'm saying. So I was talking to someone that I call Grandpa. He's much older than me. I have great respect for him, and he's really smart. Poopy Town Cat, and I was telling him that the analema is not only caused, or that my assumption, the analema is not only caused by the Earth orbit. The analema is only made by or caused by the Earth tilt, even if we had a circular orbit. And I'll show where did I get that from, Google Earth. Let's put our tilt here. This circle is 10 degrees in radius, and I'll assume that the Earth's rotation speed, uh, not the Earth rotation speed. I mean the extra rotation speed that the Earth has to do every day in order to keep looking to the sun. So let's say that after 1 day, this longitude will move from here to here. let's say that it moves extra 10 degrees every day because the sun position will change by by another 10 degrees because of the Earth orbit, and we'll presume it's a circular orbit here. And so this is at 10 degrees. uh, 10 degrees in that direction, this longitude moving from here to here, while the sun, because of the Earth movement, moved 10 degrees from here to here. It didn't cover the same longitude distance. So during the equinox or around the equinox time, uh, there is a shift, and the sun would be behind the Earth. So I don't know, that would be to left or right. But anyway, the Earth is faster than than the sun. And if we go to the topic of Cancer, summer, this is also 10 degrees, and 10 degrees on Earth or on Tropic of Cancer is different. Here is the 10 degrees. From this line to this line, it's 10 degrees because you're on a higher latitude. So the Earth is slower than the sun movement. Uh, if if there was no tilt, and the Earth just looked like that, and we bring that from Cancer to the equator, then the speed will be the same for both the Earth and the Sun. Uh, I guess that's all for now. I know it's complicated, but let me see if there's another way to do it. I wish I could just rotate this thing on its rotation axis. Uh, I don't know. So anyway, that's all for now, and thank you for watching, and thank you Soundly for coming back and coming by. Yeah, it's complicated. I'm learning it the hard way. Would you like to jump in? I don't know. You, can you come in, Soundly? The link. Where's the link? The link is this mouse. Oh, okay, okay. So anyway, did you see the declination angle video? Oh, okay. Just listening while you work. Yeah, that's okay. Uh, well, anyway, for the issue of this video, the analema on a circular orbit, am I making any sense? Yeah, I don't know much about analema, but I think it's going to help me in my Sun calc application. For 1 point, this is my Sun calc application, and I'll get the interface. So when I first made this application, the starting point was the sun elevation during zenith, and I had to get it from time and date. And then later I learned how to calculate it based on a circular orbit, and this used to get me an error by around 1.2 degrees, which I didn't like until I made the elliptical orbit calculations and wrote it accurately. And now everything here is perfect, but if you look time, I can get the length of day, the sunrise azimuth and sunset, and also the sun angles, elevation and azimuth uh, at any specific time. And when I say at any specific time, that's in relation uh, to the solar noon, which I cannot figure out. And I think that the analema, if I made the analema calculations, I can put here not just two. For example, I put two. This, if you see here, time before the solar noon, and start changing the numbers here. If I put 3, they change accordingly, and it's working perfectly. But you cannot tell me, you cannot ask me what's the angles at 11 noon in London. I will not be able to answer you. I'll have to know what's the time for the solar noon in London. So that's why I started to go into the analema thing, because I done everything with my application and I started to get bored, so I had to find something else. Anyway, I think I'll be going now, and I hope you can check the video of the sun declination angle, even just the first part, because the second part is long, and I already covered it in this video. Yeah, thank you. Okay, goodbye. يحيى انت هنا سامعني؟ انا هقفل بقى، سلام.